Okay, in this problem, I'm going to look at a projectile problem, but this time the target of the projectile, specifically the tank, is going to be moving, so that just complicates it a little bit. You want to shoot a tank that is currently 500 meters away. So here's your little tank. Put a little gun on the front of it so we know it's a tank. And it's currently 500 meters away. It's approaching you at 35 meters per second. It doesn't say anything about acceleration or anything like that, so we're going to assume that this is a constant velocity of 35 meters per second. The artillery gun is angled at 40 degrees above the horizontal. So here you are at 40 degrees above the horizontal. What initial velocity should you fire the shell at? So what we want to know is what the initial velocity is, V1 is. We can replace this V1 with the variable x. I find a lot of times students are a little bit more comfortable using x as a variable, so that's just one little thing you can do to make yourself more comfortable with the problem. If this is x, then this part is x sine 40, because this is the opposite side, and this side is x cos 40. Again, we can carry those around as they are, but I find students are a little more comfortable with them in decimal form. So if I just put sine 40 into my calculator, I get 0.643 x. And for cos 40, 0.766 x. So we don't know what the initial velocity is in the vertical and the horizontal direction, but we do at least have a relationship between them through this common variable x. So there it is. The projectile hopefully is going to go up and come back down somewhere here, and in that same time frame the tank will have moved a little bit forward, and as a result the projectile will hit the tank. Now let's summarize our information in the vertical and horizontal direction as we usually do with projectile problems. The acceleration is going to be negative 9.8 meters per second squared in the vertical, and 0, that's our usual projectile thing. V1 in the vertical, we don't know exactly what it is, but we know that it's 0.643x. And in the horizontal, again, we don't know an exact value, but we have a relationship, 0.766x. We're going to include time in both dimensions because the time is going to connect these two things. The time that the projectile is in the air is going to be the time that it takes to come down, or is the time that it has to move horizontally. And the displacement in the vertical direction, this one we know exactly. If it goes up and comes back down to basically the same height, we're going to assume it has a displacement in the vertical direction of 0. And the displacement in the horizontal direction. This is probably the trickiest little part of this, but we can figure it out looking at the problem and thinking about it. The displacement in the horizontal direction, if the tank was not moving, would have to be 500 meters. If the tank is moving 35 meters per second, then the tank is going to move in 35 meters per second times the amount of time that it takes for the projectile to fly through the air, or t as we've put it. This is a simplified thing, recognizing that acceleration equals 0. If we use the delta d, and this time we're talking for the tank, we would say that it was equal to v1t plus 1/2 at squared. The at squared goes to 0, so we really just have v1t, which is 35 meters per second. T, in any displacement by the tank, is going to come out of that 500 meters. Again, the tank is coming towards you, so if it was 500 meters away, as it moves towards you, the distance between you and it is decreasing by that 35 meters per second times time. So with that in mind, that is the horizontal distance that I want this projectile to travel. Now in these equations, you're probably noticing that I'm omitting units. And I find when you get a question like this that's a little bit complex with a couple different variables, sometimes it's useful to omit the units so you don't start mixing up variables and units. As long as you're using standard equations, the units should work out fine as long as you're working in standard units, which everything in this question is. Okay, with that in mind, I'm going to write an expression for vertical displacement and an expression for horizontal displacement and do my best to see if I can combine the two things. So vertically, my displacement is going to be equal to v1t plus 1/2 at squared. I'm actually going to use that equation in both dimensions, but vertical displacement is 0.643 x times t plus 1/2 times negative 9.8 t squared. And I can simplify this equation to be 0.643 xt minus 4.9 t squared. And one more simplification. If I factor out the t, there we go. Then I have a quadratic type of situation here where I say either this binomial or this binomial is equal to 0. T equal to 0 is not an interesting solution. That's basically saying the vertical displacement of the projectile is 0 before it gets launched off the ground, which is true, but not what we're interested in. We're interested in once it's gone up and had time to come back down. So we're interested in this root right here, which means that 0 equals 0.643x minus 4.9t. So we'll call that equation 1. We worked all the way through to get something simple to work with. Now in the horizontal direction, using the same base 5 equation of motion, my delta D is a little bit complex here. 500 minus 35t. You're 500 meters away to start with, minus the movement of the tank, which you want to account for. 0.766 xt, that's my initial velocity, times time. And here's a little bit of a break. 1/2 acceleration is equal to 0t squared, so this whole term goes to 0. So I've got two equations and two unknowns here, so a system of equations. I'm going to look for the simpler of the equations. I'm going to substitute into the other one, and then we'll work from there. Just to simplify this a tiny bit, 500 minus 35t equals 0.766 xt, and that gets us equation 2. Now let's work with equation 1 a little bit more here. I'm going to bring the 4.9t to the other side, 2.643x. And if I look up at equation 2, I can see I only really have this 1x here. So that seems like the better substitution variable. You could do the other one too, it would work out fine, but this seems like the simplest one. So if I divide both sides by 0.643, (7.62 t), and then I take that x, is that right? Yep. And then I take that x and I stick it into this equation up here. Then I can see that I get an equation that, while a little bit annoying, is solvable for t. It's a little bit annoying because it's a quadratic, but what can you do? So I'm going to just bring everything to the right-hand side of that quadratic. And then I'm just going to use the quadratic formula. Substituting everything in here. It's going to be a little bit long, but I'll just write it out for now. Now I can see I have a plus or a minus root here. If I look at this carefully, I can make my decision right now. I don't want time to be negative. I want it to be positive, so I'm going to use the positive root. If I use the negative root, I'll have a negative plus a negative over a positive. That's going to work out to be negative. Not interested in that. So I'm just going to come up with a simpler root here. Doing everything in the square root all at once here. I think I've mentioned this before, but on the off chance I haven't, it's really worth using your calculator solve the quadratic formula for you. If to solve the quadratic formula, if you are uncomfortable with doing this at all, there's depending on your calculator, you can go to other YouTube videos and see how to do that. But I can't give one solution to that because it depends on the calculator you're using. Anyways, I got 6.73 here. I just hit it all in one more time to see if I still got 6.73, and I did, so that's good. Now this equation is my simplest way of getting my 6.73 and converting it into the x, which is my initial velocity. If you go all the way back to the beginning of the question here where I made x the initial velocity. So 7.62 times my 6.73, which is what I got for the time, equals x. And my x equals 51.3 meters per second. So that's a long way, big algebraic solution, but basically, if you shoot this at 51.3 meters per second, it'll go up, it'll come down, its horizontal range will match how far that tank has moved in the equivalent amount of time. So that's a projectile shot at a moving target.